Welcome back. In this video, we are going to start chapter 1 about two important theorems in function analysis. The Arzela-Ascoli theorem, which is a result about compactness in spaces of functions, of continuous functions. And the Stone-Weierstrass theorem is a theorem about approximation or density in a space of continuous functions. So there will be two sections, and I will split the first section into two videos in order to not to make lengthy videos. So as we were saying, the Arzela-Ascoli theorem gives necessary and sufficient conditions for compactness in spaces of continuous functions. So for that, we need to do a quick review about different forms of compactness. So the first result, you probably encountered it before. It's called, it says that a compact metric space is totally bounded. What does total boundedness mean? It means that a space is totally bounded if it can be covered by a finite number of balls of arbitrary radius, or more precisely, given a positive number epsilon, we can cover the space X by finitely many balls of radius epsilon. Okay, and this is very easy to prove because we can always cover the space X by the collection of balls of variable center given radius. So the union of all these balls is X, and compactness by definition tells me that we can extract from this covering a finite subcover. Okay, so of course the center of the balls and their number depend on epsilon. So generally, if we take a smaller epsilon, we have more balls. Okay. So a space possessing this property is said to be totally bounded. So we proved that compactness implies total boundedness. The converse is not true, and you will be able to give a counterexample later. Okay. But since we shall be dealing with subsets of a metric space, totally bounded subset of a metric space, we have, so if you have a subset of a metric space, then the set inherits a distance from X, so it is itself a metric space. So it makes sense to say that it's totally bounded. And according to this definition, actually is equivalent to the following one. So A is totally bounded according to this definition, if and only if for any positive epsilon, we can find finitely many points x1, xn in A, such that A is covered by the union of these balls of center epsilon. Okay, so not quite the exact definition, because in the exact definition we should have equality for balls in A, but balls in A are intersections of balls in X with A. So just go back to the definition of the subspace topology, if you like. So this is a very useful characterization. And the second result that I suggest that you pause the video and try to solve it with a paper and a pen. A subset of a metric space, subset A of a metric space, is totally bounded if and only if its closure is totally bounded. Okay, and this is not completely, it's not difficult, you can do it, but it's not completely trivial. Okay, because we said that the center of the balls should be in the set. Okay, but in some sense, A bar is not far from A, because any point in A, for any point in A bar, you can find a point in A which is as close as you wish to it. Okay. So I suggest that you do that first. And now we clarify the connection between compactness and total boundedness, because you said they are not equivalent. For a totally bounded set to be compact, it should be complete. Okay, so there is an extra condition that we need to put. Now, so there are two implications. Compact implies totally bounded. We know that from the previous theorem. And if you recall from second year, compact implies complete. And this is not difficult to see, actually. I'll give you the idea now. So how to prove that a compact space is complete? We take an arbitrary Cauchy sequence, xn. Now, compactness, because we are working in a metric space, we know that compactness is equivalent to sequential compactness. So we know that xn has a convergent subsequence. But it's not difficult to see that if a Cauchy sequence has a convergent subsequence, then the whole original sequence converges. Okay, so let's go back to the definition. So this is half of the theorem. Now, the converse, suppose that X is totally bounded and complete. We have to prove that X is sequentially compact. So we take an arbitrary sequence xn in X, and by total boundedness, we can cover the space by finitely many balls of radius 1. So take epsilon equal 1 in the condition of total boundedness. Okay, so we have finitely many balls. Okay, now at least one of these balls, call it B1, contains all the elements of the sequence starting from a certain, for infinitely many indices n. Why? This is easy, because if each ball contains xn for finitely many indices, then we would have the whole space would contain xn for finitely many indices only, but the set of integers is infinite. So you get the contradiction. Okay. So one of these balls, I will call it B1, contains xn for infinitely many indices. And now here we have to distinguish between infinitely many terms xn and infinitely many indices, because xn could have repeated elements, but the integers are not repeated. Okay, so it's possible that there is a constant subsequence here. For example, it's possible that x1, x3, x5, x7 are all the same, but they are contained in B1. Okay, but the indices are infinite. Okay, and now so let J1 be the set of integers n of indices n such that xn belongs to B0. So what we said tells us that J1 is infinite. Okay, and don't confuse here infinity of J1 with infinity of infinitely many terms xn. Okay, and now total boundedness implies that we can cover X with finitely many balls of radius 1/2. Of course, we have a bigger number now. It's only finite. Okay, since J1 is infinite, then again, at least one of these balls, I will call it B2, contains xn for infinitely many indices in J1. Okay, so first we use the infinity of n star. Now we use the infinity of J1, and you guess where this is going. Okay, so we let J2 be the set of integers in J1 such that xn is in B2, and I continue this. So as the case step, we let Jk be the set of integers in the previous set such that xn is in Bk, where Bk is the ball of radius 1 over k and Jk is infinite. So we repeat this to infinity. So what do we get? Now we'll construct the convergence subsequence. So first, take an element n1 in J1, and by induction, given nk minus 1, choose nk in Jk, of course bigger than the previous one. This is possible because each Jk is infinite. So no matter how big the index that we take, we can find a bigger index. Okay, so what do we have? If we take I and j, two indices bigger or equal than k, ni and nj by construction belong to jk, because jk is decreasing. Okay, so actually n sub I belongs to ji, but j sub I belongs to jk because this is an decreasing sequence. Okay, so J1 contains J2, contains Jk, and so on. Okay, so the points xn sub I and xn sub j belong to the ball bk by construction of jk. Okay? If ni and nj are in jk, then xni and xj are in bk. And that's it. So the distance between these two terms is less or equal than 2k. So x and I, this sequence, when I let I vary, is a Cauchy sequence because I can take k to be choose k to be as large as you wish. Okay, and that's it. Now, completeness of x dictates that this Cauchy sequence must converge. So we found a convergent subsequence of the original sequence, and that's it. So this is sequential compactness. Okay. Therefore, in a complete metric space, a subset has compact closure if and only if it's totally bounded. Okay, so proof. So let capital X be a complete metric space and consider a subset A of X. Suppose first that A bar is compact. Then, according to the first theorem, A bar is totally bounded. But according to the lemma that I didn't prove, A is totally bounded. So this is one way. So in a complete metric space, but this is actually, you don't need the completeness here, actually. So one way, don't. Now for the converse, we need completeness. If now A is totally bounded, then according to the same lemma, A bar is totally bounded. But if the space is complete, then A bar is also complete because it's closed. So it is itself complete. So what do I know now? I know that A is totally bounded and complete, and according to the previous theorem, it is compact. So the closure of A is compact. Okay? And a space, a subset having a compact closure is said to be relatively compact. For example, the open interval 0, 1 in R is not compact because it's not closed, but it is relatively compact because its closure, 0, 1 closed, is compact. Okay. And we can formulate this result in a slightly different way. If we have a metric space and a subset A of this metric space, then A is relatively compact if and only if every sequence of A has a convergent subsequence. Now, it seems that it's just a tautology, but it's not completely a tautology because we didn't specify where the limit is. Okay? If the limit must be in A, then A is itself compact. Okay? Then we are repeating the same thing. But when we say that every sequence of A has a convergent subsequence, the limit actually is in the space, and we know that it's in A bar because by the characterization of A bar. Okay, but so the limit belongs to A bar, but not necessarily to A. Okay, so try to prove this as an exercise. It's a corollary, actually. And in Rn, because in Rn we know that a subset is compact if and only if it's closed and bounded under any of the usual distances, we have equivalence here. So for a subset A of Rn, saying that A is bounded is the same thing as saying that A is totally bounded, and it's the same thing as saying that A is relatively compact. Okay. So usually 3 implies 2, 2 implies 1 in any metric space. Okay. But because if A is bounded, then A bar is bounded. And so A bar is closed and bounded and therefore is compact. So this is why 1 implies. So you can do a circular proof here if you like. But this is not true in any. This is true in spaces where compactness is equivalent to closed and bounded and boundedness. Okay, and now we move to our main subject, which is the space of continuous functions between two metric spaces. Usually we'll take the first one to be compact. You'll see why we need compactness of X. And most of the time we'll assume that Y is complete. Okay, so if you have two metric spaces, X equal to the distance d sub X and Y equal to the distance d sub Y, the set of all continuous functions from X to Y is denoted by Cxy. Okay, this is an extension of the space C01 of continuous functions from 01 to R. Okay, it's a very particular case. Now, if this source space is compact, then we know that every continuous function is bounded and achieves its bounds. So if f and g are continuous, we know that the distance of y as a function of two variables is also continuous with respect to itself, with respect to the topology it generates. So if you consider this map d of fx gx as a function of x, everything is continuous here. So this is a continuous function. If the space is compact, this function is bounded. So we can talk about its supremum, which is a maximum actually. Okay? And this quantity, we call it delta fg. And it's very easy now to check that this is a distance. So it satisfies the 3 or 4 properties of a distance. It's non-negative. It's 0 if and only if the two functions coincide. It's symmetric and satisfy the triangle inequality. So it's very easy to check. So this is where we need compactness in order to ensure the finiteness of this quantity. Because if the space is not compact, this could be plus infinity. But usually distances are not allowed to take the value plus infinity. Okay, so compactness rules out this possibility. Now, most often, as we said, we'll assume that X is compact and Y is complete. Then it's easy to prove that the space Cxy is also complete. Okay, it's just very similar to the proof that C of 01 is complete. If you already know it, you can skip the proof, but it's not difficult. So go back to the definition. We take a Cauchy sequence Fn in the space, and we write the condition of Cauchy sequence means that the distance between Fn and Fm is less than epsilon. But since this distance is the supremum, this means that this condition holds uniformly in X. Okay, so we have something more than just a Cauchy. We have a uniform condition of Cauchy because the n0 depends only on epsilon, not on X. Okay, so it's a uniform Cauchy condition. So in particular, if we fix X, the sequence, we have a sequence Fn of X, which is a sequence now in Y. But since Y is complete, this sequence is convergent to some limit. But this is true for every X. So we get a new function that I call f of X. Now, I need to prove two things, that f is indeed continuous as a function of X. So when X varies, we get a continuous function. And second thing, Fn converges to F. Why do we need to ensure that F is continuous? In order to ensure that F is in is in the space Cxy. Okay? So two things, F is continuous, so belongs to the space. And second thing, the distance between F and F tends to 0. Okay. Now, the first condition is, I think you encountered it before in some course of analysis. We use the triangle inequality. So first of all, we pick epsilon, and we take n0 to be as in this condition 1. Okay, so n0 depends only on epsilon and not on X. Okay, and now if you look at this condition 2 of convergence, actually here, we want to prove that actually. How do I prove that? So if in condition 1 we fix everything n, m, n0, etc., and we let m tend to infinity, what happens? Since the distance is a continuous function of two variables, if fm of x converges to f of x, so this quantity converges to the distance between fn of x and f of x. Okay, so if in condition 1 you fix everything and you let m tend to infinity, okay, we get the distance between fn of x and f of x is less than epsilon. But this is true for every x and n0. So we proved actually 2. So this means that fn converges to f uniformly. Okay, so this is the first thing. And now I use this claim to prove the continuity of the limit. Continuity at every point. So pick an arbitrary point x0 in the space and let epsilon be positive, arbitrary. So choose n0 as in condition 1, as we said. And now we use the triangle inequality, as you probably know. We want to show that the distance between f of x and f of x0 can be made arbitrarily small, provided x is sufficiently close to x0. So I use the triangle inequality. I introduce fn0 of x and fn0 of x0. So I have the triangle inequality implies that this distance that I want to, for which I want to an upper bound, is less than all these three, the sum of all these three terms. And now I prove that each of these three terms can be made less than epsilon if I like. The first one is less than epsilon. Why? According to condition 2 that we proved. And similarly for the third one. So by 2, the first and the third are less than epsilon. Now, what about the middle, the second term? The second term actually can be made less than epsilon by continuity of fn sub 0. Okay, because each fn sub 0 is continuous. So we can find a positive number eta that depends actually on n0 and on x0, because we don't have uniform continuity. Actually, we have it because because continuity on a compact set implies uniform, but we don't know that yet. Okay, so if the distance between x and x0 is less than this positive number eta, then this quantity is less than epsilon. So combining everything together, if the distance between x and x0 is less than epsilon, then the distance between their images is less than 3 epsilon. And since epsilon was arbitrary, this precisely means that f is continuous at x0. Okay, so now if I wanted to have here epsilon, I should have taken here, this is less than epsilon over 3, this is less than epsilon over 3, this is less than epsilon over 3. But this is not necessary, because if I prove that something can be made less than 5 epsilon or 4 epsilon or 100 epsilon for every epsilon, then this is true for every epsilon. Okay, so don't need to have precisely this epsilon. Okay, and last thing to prove. So now f, we know that f is continuous on the whole space because x0 was arbitrary. And now if I go back to condition 2, since this holds uniformly in x, I just take the supremum over x here. And I get the distance between fn and f is less than epsilon, okay? And therefore, fn converges to f with respect to this distance. So fn converges to f in the space cxy. Okay, so, and I think I will stop the video here, and I will continue in the next video where I will formulate 2 conditions that are necessary and sufficient for relative compactness in the space cxy, which is a space of functions. So thank you for your attention.